Thank you. Thank you for the introduction. So, good morning, everyone. First of all, I'd like to sincerely thank Professor Panigrahi for inviting me to speak here today. It is a pleasure to have the opportunity to share some of our recent work in this fascinating area of quantum thermodynamics. So, the title of my talk is Measurement-Based Quantum Thermodynamics. So, this, by now, many of you already know that quantum thermodynamics is one of the most fascinating and youngest area in this quantum physics or quantum technology. So it sits at the intersection of three fields that have individually transformed science over the last century. The three fields are quantum mechanics, thermodynamics, and the quantum information theory. So classical thermodynamics was developed to understand the steam engine during the Industrial Revolution. Today, however, technology has progressed to a point where we can manipulate single atom, ions, photons, superconducting qubits, and spins. So basically, there is a miniaturization of the technology. So naturally, this raises a very important question that can a single quantum particle behave like a quantum heat engine? So if the answer is yes, then many other questions immediately follow. The first question we can ask is that what do we mean by the heat in quantum mechanics? What is work? How work is defined in the quantum domain? And can quantum coherence improve the engine performance? And also we can ask, can quantum measurement themselves become the one of the thermodynamic resource? The last question is the main theme of my talk today. So the central idea I want to convey is actually very simple. A quantum measurement is not merely a way of obtaining information. Okay, we do measurement to get some information. So a quantum measurement here is not merely a way of obtaining information. It also acts as a physical resource for energy and entropy for a system. Okay, so my talk is measurement-based quantum thermodynamics. So what today's talks cover? So today's talk will cover three main points. I will discuss very briefly that what is the foundation of quantum thermodynamics, how heat, work, entropy they are defined, and how quantum thermal machine are implemented in this domain. And especially I will focus on the Otto engine, the Otto cycle. Next, I will show that I will focus on the main theme of this of today's talk, that is the measurement idea. So why this measurement idea was required, and why this quantum strokes, the traditional strokes for a heat engine, quantum heat engine, they are problematic, and how a measurement can solve the problem, how a measurement can actually replace one of the path. And then I will, in the final part of my talk, I will discuss about my two recent work on this measurement-based quantum thermal machines. Okay. So the quantum thermodynamics. So let me first discuss about the, the foundation part of this quantum thermodynamics in a very brief manner. So this field, this quantum thermodynamics, it lies in the intersection of a very, three basic field in science, that is quantum physics, information theory, and quantum thermodynamics. So we know, quantum mechanics or quantum physics. So it relies, how it is different from classical physics is because of the superposition principle. Okay, so quantum states can live in a superposition state, and that actually gives rise to the coherence. And if you consider two quantum bodies, okay, then this coherence actually leads to entanglement. So they are the main quantum property which doesn't have any classical analog, and we try to use this quantum property as a resource in the field of quantum thermodynamics. Next is information theory. So traditionally, in the beginning, we thought that information is a very abstract idea. Okay, information is something very abstract. But with the beginning of Shannon's work and later with this Landauer's principle, it is realized that information is nothing abstract. Information, we should call information is physical, because information can be stored in a physical system. Information can be erased. It has entropy, and erasing information has some energy cost. So information theory tells us that information is physical, and that has a very big impact in this area of quantum thermodynamics. Next is, So next is thermodynamics. Okay, so I should not have written this orange circle as quantum thermodynamics. It should be thermodynamics. So thermodynamics is a, very, very well established area of physics. And we know that basically it works in the many body system. Okay, so it's a macroscopic theory. Thermodynamics is a macroscopic theory, but thermodynamics teaches us how heat, work, entropy, irreversibility, and energy conservation work in a big system, thermodynamic system that we call. So quantum thermodynamics attempts to merge these three viewpoints into one consistent framework. One sentence beautifully summarizes this philosophy, that information is physical, and that is our key point here. Okay, so the next question is, then what is quantum thermodynamics? Okay, so in classical thermodynamics, we know that we deal with big system. How big? So generally a gas contains, a container containing a gas, so contain of the order of 10 to the power 23 particles. Okay, so at such scale, whatever there is small fluctuation, this microscopic fluctuation, we don't care about any microscopic fluctuations. So all the macroscopic fluctuation averaged out in the thermodynamic scale. But since today, as I have already mentioned, that we are now, successful in manipulating single atom, single ion, single superconducting qubit, two interacting spins, etc. So the question arises that does the laws of thermodynamics, the classical thermodynamics, are they valid in the quantum domain or in the in the quantum limit? So interestingly, so we can ask the question that how do the laws of thermodynamics change when the working substance consists on only few particles, few quantum particles specifically? So interestingly, it has been seen that an equivalent first law of thermodynamics, we can also find the equivalent first law in the quantum domain. Okay, we can rewrite the second law. Second law of thermodynamics is also valid, and we can rewrite the second law. Okay, in terms of von Neumann entropy, in terms of quantum entropies, that is the von Neumann entropies. New phase transition, domain is found. Okay, phase transitions, they are quantum critical points. So they are another main, control point in the control point of the quantum thermodynamic behavior at T equal to 0, absolute zero temperature. And also, we can find new thermal machines, in the quantum domain. So thermal machines are like, they can be refrigerator, they can be engines. Okay. So with the quantum system, where we use the quantum system as the working fluid. So basically, so far we have understood that the main difference that from a quantum, classical thermodynamics, got classical machines, thermal machine, and quantum thermal machine. That is the instead of a gas or a fuel in the cylinder, we use a single atom, single ion, or a few quantum particles. So as my working fluid. Okay. So I again come back to the point that information is physical. So this idea actually, started with Shannon's work on information theory. So we earlier knew that entropy, entropy reemerges as a measure of information, the same functional form as thermodynamic entropy. Okay, so earlier we only had the thermodynamic entropy. So in the with the beginning of this information theory, Shannon identified that there is another entropy called the information entropy, and they look similar. Okay, with the thermodynamic entropy. Later, Landauer said that, it is not only in the mathematical definition, information is also physical. It can be shown that, erasing one bit of information dissipates at least kT ln2 amount of heat. So logical irreversibility has its thermodynamic price. Okay. And then there is this Maxwell's demon. Okay, so Maxwell. If you know about this Maxwell's demon, where this considering a single cylinder, single box containing a gas of moving particle. Okay, and so using, there is a demon who can identify and separate the slow moving particle and the fast moving particles. And it can, extract work using a single bath. So, which contradicts the second law of thermodynamics, but with the Landauer principle, it was resolved that this Maxwell, the demon's memory has to erase. Okay, we have to erase the memory of the demon, and to erase that memory, we have to pay the cost. Heat will be generated, and that actually resolves the paradox. So this establishes the fact that information is physical. So manipulating the information. I'm trying to, through this slide, I'm trying to establish the fact that how measurement is important. Measurement is related to information. So manipulating information is also done by measurement. And since measurement manipulates information, and that it is also related to the thermodynamic process with real energetic cost and benefit. So this is how information is related to the thermodynamic process. Okay, so next we discussed about the heat, work, and entropy in quantum thermodynamics. Okay, so in classical thermodynamics, from the first law, we know that this if U is the internal energy, so dU is equal to dQ plus dW. Okay, so dQ is the heat change and dW is the work done. So the equation look very simple, okay, but in quantum mechanics, we need to define precisely what we mean by heat and work. Okay, so the internal energy is defined in quantum mechanics by U is equal to trace of rho H. H is the my energy operator here, and rho is my system state. Okay, so we know that trace of rho H will give me the average energy. So that is defined as U. So now if you do the if you calculate dU, so you will get two terms. One is trace of rho dH and another is trace of d rho into H. So the first term, which is trace of rho dH, so that actually define the work done. So this dH, we are keeping my quantum state as it is. Rho is not changed. dH is the energy change. So energy change is done by moving the energy level. Okay, so that means we are changing the Hamiltonian, and that is equivalent to doing some work done. Okay, and this change in Hamiltonian can be done by some application of external field. So changing the field, you can change the Hamiltonian. So this is equivalent to work in quantum thermodynamics. And the second term, which is trace of d rho H. So here we don't touch the Hamiltonian. Hamiltonian is, it is remain as it is. It will remain as it is, but d rho, it reflects the change in population. So population, there is a redistribution of population. Okay, so this is actually, so whenever population is redistributed, so entropy will change. So this will, this term is defined as the new heat term. Okay, so trace d rho H is the heat term. Okay, so because a projective measurement changes the density matrix without changing the Hamiltonian, it contribute through the heat term. So this single observation is the entire foundation. Again, I'm trying to insist on this point, that this observation that the changing the rho or changing the population can actually, it gives rise to this heat term. So this observation is the entire foundation of the measurement-based thermodynamics. How we will come to that point very soon. So finally, entropy is measured as trace rho log rho, and the second law is rewritten as delta S greater than equal to beta Q. Beta is inverse temperature, and here this S is defined as minus trace rho log rho. Okay, it is the von Neumann entropy. Okay, so before discussing the quantum engine, let us briefly remind ourselves how ordinary heat engine work. So every heat engine requires two ingredients, one hot bath, one cold bath, hot reservoir, cold reservoir, and heat flows from the hot to cold, and there is a system or the fuel working system in between. Okay, so part of this heat that flows from the hot bath hot reservoir to cold reservoir, so it is converted into useful work. So the Carnot engine provides the maximum theoretical efficiency, which is 1 minus Tc by Th. The Otto cycle consists of, Otto cycle is another variation of a heat engine. Okay, so it is a four-stroke engine. There are two adiabatic stroke and two isochoric stroke. Okay, and the efficiency is given by this eta. Okay, 1 minus V1 by V2 to the power gamma minus 1. And here heat exchange only occurs at fixed volume, that is during the isochoric strokes. Okay, and the opposite of a heat engine is a refrigerator. Okay, it is run in the reverse direction, and in case of refrigerator, we calculate the coefficient of performance. So they are traditional heat. Very quickly, how a traditional heat engine looks like. Okay, so now let us talk about this Otto cycle. So the Otto cycle has, as I mentioned, it has this is a four-stroke engine. So there are two isochoric stroke, okay, and two adiabatic stroke. Just a moment. Yeah, so so if you start from point A, so there is a hot isochore where the system is connected with the hot thermal bath. Okay, so and here it exchange heat with the hot thermal bath and comes to an equilibrium. Okay, and so system expands and exchange heat with the hot bath and come to an equilibrium, and then the system disconnect from the hot bath in this adiabatic stroke. So there is no heat exchange. So, and here the external field is, there is a adiabatic expansion. Okay, so by the external field, controlling the external field, and work is done in this adiabatic expansion. Next is another isochoric. So this is the cold isochoric part. Okay, so here again it is connected to the cold bath. So this cold bath can be controlled. Can be replaced by measurement cooling. That again we will talk elaborately in the coming slides. And the last stroke is the adiabatic compression, where again it is disconnected from the cold bath, and it is through adiabatic compression it comes to the initial point. And this external field can be this working system. So here can be a qubit or spin. Okay, so that can be a working substance, and your external field can be the magnetic field. Okay, so isochoric strokes occurs at fixed magnetic field. Okay, and then in adiabatic expansion, the magnetic field is changed from a lower value to a higher value, and in the compression, the magnetic field again is changed from that higher value to the initial lower value. So the eta auto can be calculated as 1 minus BL by BH. BL is the lower value, BH is the higher value of the magnetic field. Okay, so the point is, I mean, what is the necessity of going to this quantum part, quantum auto engine? So already, I mean, I have given some insight that why we want to go to this quantum domain, but there are some other actually other interest that actually drive people to think about this going to the quantum domain. One is, I mean, because as quantum mechanics has some special property like coherence, correlations, or entanglement, and there are which we call as resources, quantum resources. So the main question is, can this quantum, just without thinking that we are just replicating or the classical heat engine to a quantum domain, can these quantum resources can enhance the performance of the engines or machines? So that is another intriguing question that make us work in this field. Okay. So we know that coherence comes from the superposition principle. Superposition in the working state can lift work output beyond the naive classical limit. Okay. Next is correlation. Correlation, coherence is also a kind of correlation. Here we are talking about correlation between two quantum bodies. Okay, so which we know as entanglement. So we know that entanglement between two, when two quantum bodies are entangled. So if you do some change in one of the of the part, so it will affect. Do some change means do some measurement or something. So it will affect the other part. Okay, so this actually, you can control by doing some measurement to one of the part. You can control the thermodynamic change in the other part of the body. Okay, so this also used as a quantum resource. Okay, next is engineered bath. So in classical domain, the thermal environment, they are itself engineered. I mean, we cannot do anything with that. Okay, baths cannot be in the classical domain. Thermal bath cannot be. We can have squeezed bath, coherent bath, or otherwise non-thermal bath. So again, that means there are some. We can produce some kind of correlation inside the bath. Okay. So that and the back action of the bath to the system can also act as a resource. And then we can, in classical engine, we work in the, infinite or quasi-static limit. Okay, so in quasi-static limit, first of all, this there is no power. We look into the focus into the efficiency only, but because time is infinite, so there is no power output. But if you in quantum domain, if you work in this, you can work in this finite time. So finite time means before that the system completely thermalized with the bath. So once it is thermalized with the bath, so its all coherence will be gone. It will be in a mixed state, completely mixed state. So, but if you stop the stroke before it thermalizes completely, so that is my finite time limit. So then it will retain some coherence in it, and that will give me some, may give us some enhancement in efficiency and also give us non-zero power. Okay, so there are few landmark results that I want to discuss here. So one is this, the very one of the original work here is the work by Scully et al. In 2003, where they have shown that coherence in the working state, okay, working system. Okay, so because of the coherence of the working system, it can enhance the work output beyond the Carnot limit. Okay, so it was one of the first work in this towards this direction. Okay, then Uzdin, Levy, and Kozlov in 2015, they have shown that coherent quantum engine can outpower classical stochastic ones. Okay. Entanglement, then in 2015 also, they have shown that a quantum thermal machines, using a 2-qubit working fluid, they can generate bipartite entanglement. So quantum thermal machines can used as a entanglement generator. Okay. And also in 2014, people have used a squeezed bath, which is a kind of engineered bath, and showed that an auto engine with a squeezed thermal bath can exceed Carnot efficiency. So these are, it is of course not the, complete review of work. So I have just taken some important work in this direction. So, so now coming to our work, so which is the part where it is, why it should be measurement based, or why we thought of this kind of idea, is that in the standard recipe, what we have shown that suppose we are running a quantum auto engine. So there are, two strokes, so where this isocodic stroke, where it has to connect alternatively. First, it has to connect with the hot bath, and then it has to be switched off, and then it has to connect with the cold bath. Okay, and then again it has to be switched off. So we have to please remember that we are manipulating a quantum system, like a single ion, single qubit, okay, single spin, single superconducting qubit, like that. Okay, so and we are talking about, there are two baths, and we can switch on or switch off the bath at our wish. Okay, alternatively we can do that on demand. But for microscopic engine, for macroscopic engine, this idea is fine. We can physically connect or disconnect pipes or valves, etc. But what about nanoscale quantum system? Okay, so as I gave the example of superconducting qubit, a superconducting qubit is always embedded in an electromagnetic environment. Okay, a trapped ion always it interacts with the surrounding electromagnetic fields. Okay, a spin inside a solid, if you talk about the single spin inside a solid, it always interacts with its neighboring spins. Okay, so environment is never absent. It is always on, right? So it is always there. So therefore, we cannot simply turn off or turn on the interaction with the environment. It is already on, always on. And also, even if we could do that, rapidly switching off or switching on the environment, this interaction with the environment, itself, it will introduce additional energy cost. So anyway, I mean, it is not possible. Practically, it is not possible. So it may create unwanted excitation, non-adiabatic transition, and all those things. So is there any other way of implementing the cold stroke or the hot stroke? At least, keeping the bath always on. Is that any other way of implementing the engine? Okay, so that is the motivation of our work. Okay, so here we thought about how about see, the hot bath is always there, environment is always there for a single qubit or single spin. How about this? Keeping it on, always on. Replacing the cold bath using a projective measurement. Okay. So suppose I perform a projective measurement and find the system in its ground state. So what happened? So if I do a projective measurement and project the system in its ground state, okay, so the entropy will decrease, okay, and heat will be released to the bath, right? So this is actually this process mimics the cold bath. Okay, in the cold stroke, heat is released, right? So here, so projective measurement can replace this. Projective measurement to the ground state actually mimics cooling. Similarly, if we do a projective measurement in the excited state, entropy will increase, and it actually similar to heating the system. We can do a non-selective measurement as well, where we do not care about, what is the output. Okay, so these first two examples were their selective measurement. If we do non-selective measurement, it also, there is heating as well as, this population will redistribute. So work distribution will also be there. Okay. So the moral of the story is cold stroke can be replaced by projecting the system to its ground state. Heat and work, so excited state projection injects energy, non-selective measurement heats and reshapes the work distribution. But there is a cost, of course. Measurement is not free. Or I have already said that measurement is measurement means I am erasing some information. Okay, measurement collapse the quantum system, so there some information will be lost, and information loss will follow energy cost. So measurement is not free. It carries Landau type cost. It removes the need for the but at the same time, it removes the need for the second reservoir. But of course, while calculate the efficiency, we have to take into account this measurement cost. So there is certain trade-off. So I want to emphasize here that nowadays, there are in last 5-6 years, there are many works on measurement-based quantum heat engine. But our group was the first to show this path, and we were the first who worked on this measurement-based quantum heat engine. And I started this work. Basically, Suman did the first work on this. There were 3-4 paper, first paper. Suman started his work on single traptan. Okay, so here we considered both the electronic and the vibrational degrees of freedom as the working fluid, and the vibrational modes, they act as a cold bath. So we did the measurement, and the heat is released in the this vibrational modes. So projective here, the main focus was the projective measurement mimics the heat release. And Suman first worked with the single trapped ion, and then we did. There was two ion, and we analyzed the critical point behavior, and also the finite time auto engine was analyzed. And then with Chayan, my another former student, so I worked with Chayan, where apart from other type of analysis, he did one work based on this measurement-based heat machines, where he analyzed the Starling engine, not the Otto engine, the Starling engine with anisotropic coupling. And he worked analyzed the non-adiabatic behavior towards the efficiency at finite times. So, this final part, I will discuss my work on. Of course, this work is done with my present student Ratnakaran. So he is doing very well. So the main focus. There are two work that I will discuss. The first work is by Ratnakaran, where he actually analyzed the ancilla measurement based quantum auto engine. Okay. Okay. So here the structure is like this. So you can see there are two coupled qubit pairs, okay, Q1, Q2. So this is a ladder kind of system, okay, 4-spin ladder system. So there are two working qubits, Q1, Q2 are their working qubits, and this Q3 and Q4, they are the ancilla. So together it is the whole system, and they are connected to a common bath, okay, hot bath. And this Q1 and Q2, they are they are connected by this J1 coupling, and Q3 and Q4, they are connected by this G2 coupling, and this system and ancilla, they are connected by this G coupling. Okay, so here is the ancilla Hamiltonian for the ancillary system. The system Hamiltonian is this. So they are connected by XY coupling and through J1, and there is a driving magnetic field. So that is the Z coupling, Z interaction. Okay, and also there is another drive through which there is the exchange interaction. Delta 1 is the another drive for exchange interaction. Okay, so this is the system, and here the main focus was that that you can we have analyzed both the situation where first we do the this projective measurement on the system, which is Q1 and Q2 in some basis, okay, and or you can do the measurement on Q3 and Q4. So because they are all connected, okay, and this Q3 and Q4, they are entangled with this Q1 and Q2. So ancilla is entangled with the this system. So if you do the measurement on the ancilla, so that the benefit of that is first measurement will replace the cold measurement, and in the proper basis will replace the cold bath. Okay, so that will take care of the cooling process, and also since we are doing the measurement on the ancilla, it will not disturb the system. Okay, so that is the main thing. So we can use this ancilla as an external knob. We are not disturbing the system. by measuring on the ancilla, we are using it as an external knob to control the efficiency and to operate the engine. Here we have seen that there is a phase transition point, that when the field strength is equal to the field strength B is equal to this interaction strength J1. So there is an abrupt change in the ground state. Okay, there is a level crossing. Okay, and first order level crossing, which actually signify a quantum critical point. And at the in the region of this quantum, in the neighborhood of this quantum critical point, there is this ground state become degenerate. Okay, it becomes doubly degenerate. And now if we apply a transverse field, delta 1 and delta 2, okay, so that acts like, it leaves this, mathematically they are known as this Landau-Jenner term, and they lift this degeneracy. Okay, so they split the degeneracy. Okay, and in this region, quantum fluctuations are strongest, and the engine's efficiency sharply enhanced there. Okay. So here we show, this is a plot of efficiency versus power versus this tau is the adiabatic time scale. So as the the more is the tau, okay, as tau increases, we are more towards the adiabatic limit. Okay, so if tau is small, so that reflects the non-adiabaticity in the system. Okay, so you can see there are some fluctuations here, oscillations. So they are because of this this low tau. Okay, so they are the reflection of non-adiabaticity in the system. So we can see that when this G is 0, okay, and delta 2 is also 0. So in this region, there is, this is this red curve. Whereas as soon as you make the connection with the ancilla, okay, so this ancilla, whenever you start, give entry to the ancilla, you make this G non-zero, then this efficiency suddenly increases. Okay, this efficiency and that happens. So after some but if you increase your tau more, then it saturates, and power also do not increase anymore. So this is your working region. Efficiency 0 to tau 0 to 10. In this box, you see this is your working region where you can increase and control your efficiency by changing this. And it goes above the original auto limit, which is 0.5. So here actually we again, what I have already mentioned about this knob, external knob. So measuring the ancilla pair rather than the system, it gives us the flexibility that controlling the engine by some external knob. The measurement basis, proper choice of the measurement basis is also important. That also modulates the efficiency of the working medium. So this work was published in Physical Review E. So in this work, we established that 1 bath is enough, and we can go beyond auto limit by local control of the ancilla. And with inter-pair correlation, we can push the efficiency above the standard quantum auto limit. Criticality is the, this hidden gem here, okay? And Also, I mean, always on, I mean, everything comes at a price. So keeping the bath always on is, of course, a feasible thing, but that comes with the price of measurement. So measurement cost has to be included. So another very fascinating work that is the present work which is under review. So this is the squeezing fueled quantum auto engine. In the beginning of my talk, I talked about engineered bath, where I talked about squeezed bath. Okay. But here I'm not talking about squeezed bath, rather squeezed fuel. Okay, so that means the working system is squeezed, not the bath is squeezed. Okay, so in this work, we are going to talking about three main quantum resources. One is non-Markovian bath. Okay, Markovianity means, I mean, when system, generally we talk about Markovian limit. Markovian limit means there is no memory of the system. Whatever information is lost in the bath, so that is gone permanently. There is no coming back of that information. Okay, but if we work in the non-Markovian regime, that means information again comes back. I mean, to the system. Okay, so I mean, the information is not completely lost. So there is some correlation. So we will talk about non-Markovian bath. So a single structured reservoir modeled exactly where memory effects retained and it is not averaged away. Then measurement induced cooling. So by now we understand what is a measurement induced cooling is. So that is also a resource. And our third resource is squeezing as fuel. Okay, so squeezing, we know that squeezing is typically a quantum phenomena where one of the quadrature becomes more uncertain than the other quadrature. Okay, like considering the position and momentum quadrature. So by squeezing, we can make it more one of the quadrature more uncertain than the other one. In other words, by squeezing a field means these photons are, I mean, you are changing the photon statistics. Okay, you are redistributing the photon distribution. Okay, so a squeezing operator on the cavity mode injects non-passive free energy. Okay, so I mean, here squeezing acts as extra free energy. Okay, and it is typically a quantum resource. There is no classical analog of this. So here is the system that we are talking about. So this is our system. So here we consider two qubits. They are connected by some coupling, and and also they are in a single cavity, and they both are connected with the cavity by a common coupling G. Okay. And the whole thing, this cavity and the two qubit, so they are all coupled to each other, and yeah, they are all coupled to each other, and they are immersed in a hot bath, a common hot bath here. Okay, and here we will do the measurement on the system. No, not on the system, on the cavity. Okay, the projective measurement will be done on the cavity to replace the this cold bath. Okay, so the working substance is two interacting qubits to a single cavity mode, and this model is called the famous quantum Rabi model. Quantum Rabi model is the, I mean, fundamental model in cavity QED kind of a system. Okay, here the main point is I mean, this Hamiltonian on certain condition, that is, I mean, we can, this Hamiltonian can be block diagonalized, and it can be separated into two part, asymmetric and an antisymmetric part. We can divide it into, and we work with the symmetric part. Okay, because the antisymmetric part is is not useful here, so we can work with the symmetric part. Okay, and that actually this possibility actually makes us possible to get some analytical result to get get the efficiency in terms of the squeezing parameter. Okay, so we give some analytical result. So here the qubit coupling produces first order phase transition. So there are some built-in criticality that also sharpen the thermodynamic control. Here, because we are working in the non-Markovian regime, so doing the numerical work is not easy. So so here we model the hot isochore using this hierarchical equation of motion, HUM method. Numerically, we use this method to do the exact treatment of non-Markovian bath, keeping the system bath correlation beyond this Markovian limit. Okay, and then this projective measurement is done by doing measurement on the displaced cavity Fock states, which cools the qubit through back action. And here we are using an extra energetic fuel, that is the squeezed cavity. So squeezing the cavity mode injects non-passive free energy. We have shown a perturbative treatment which yields closed form expression for work and heat versus squeezing strength and phase. So here are some numerical results. We have plotted here the eta and p, and this is done for different values of squeezing parameter. So you can see that as we increase the squeezing, we do not increase the squeezing very much. So but as we increase the squeezing from the non-zero value, both this power and efficiency, it increases monotonically. And also we have seen that there is this efficiency is not only dependent on the absolute value of this squeezing parameter R, but also the squeezing phase phi. So there is a trade-off between these two. So a practical engine should not be just a one cycle engine. So it should stabilize for many cycles. So here we have done the analysis for many cycle limit. So you can see we have gone up to 30 cycles. Okay, so here we show that how the engine stabilizes when we go to the many cycle limit. Okay, so here you can see we have plotted energy balance on one hand, and here is dn is the trace distance between the after the fourth stroke, the final state of the working system and the initial state of the working system. So the trace distance between this is represented as dn. So you can see that as you increase the cycle number, so after many cycles, the trace distance almost goes to 0. Okay, so that means system initializes very well to its initial state after each cycle. So that is very, so the system is, this engine is working in a very balanced way. So what this work established is that squeezing as a non-passive energy, okay, so it is working as a fuel measurement pools in cavity QED, a multi-resource engine, okay, where here we have used, not only single resource, there are 3-4 different resource, quantum resource, and which can combine well with each other. And our model is experimentally feasible model. Okay, so far, measurement based. There is no experiment in this direction, but our model is experiment ready. So anyone having the experimental setup can conduct this kind of cavity QED experiment with this kind of model. How much time I have? Maybe I am exceeding the time.
Yeah, you are exceeding the time by 1 minute. You don't have.
Okay, so maybe yeah. So I will just conclude. In a very within 2 or 3 minutes. So and there are some in the future, or also we are working on this quantum thermometry part. This is also a very interesting direction in quantum thermodynamics. Because why? Because quantum thermometry is important. One of the bottleneck in quantum thermometry is we want to measure the temperature of a suppose a quantum bath or quantum system, but temperature is not an observable in quantum mechanics. So there is no operator for temperature. So how to do the parameter estimation using this measurement based idea. So that is one of the main focus of this kind of work. So there are a few work on quantum thermometry. So where actually we use the temperature sensitivity using the Fisher information. So there is this Kramer-Rao bound for that. And so here our idea would be, we can use a spin chain as a conductor, as well the spin chain as the thermometer. So and we will try to estimate the temperature by locally measuring the spins in the spin chain. So that is the work is in initial level, but we are working towards this. So the take-home message is measurement can replace a bath, finite time can beat quasi-static, criticality helps, and resource they compound, they complement each other. Many resources they stack together. Okay, so there are some open direction. What happens if we scale to n spins, whether n spins is better, more spin is better, or it will not give any benefit. We generally work with bosonic bath. So spin, what happens if we use spin bath? Then what class of measurement are physically feasible on spin chains, and which maximize the extractable work, like that. So this is my present group at IIT Ropar. Jatin, Ratnakaran, Sania. Sania is in her second year only. And they are my former students, Anil, Devender, Manju, Suman, and Chan. So Suman and Chan, they worked on quantum thermodynamics. Okay, thank you. Thank you for your attention. So I'm open for question and discussion.
One question. So,
yeah, go ahead.
Clarification. So first of all, thank you for a very interesting and informative talk. Could you remind or briefly remind benefits of in terms of reinterpretations or new physics by using quantum thermodynamics in quantum technologies?
Yeah, as I mentioned that the benefit, I mean, there is two perspective of doing quantum thermodynamics. Is one is the necessity because of this quantum technology in quantum systems, if you want to do heat management, then quantum thermodynamics is the area which should be explored. Another thing is what is the benefit? So extra benefit is that, I mean, it is already proven, at least theoretically, that this quantum resources like correlations, superposition principle, I mean the entanglement, and they can enhance the efficiency beyond the this ideal auto limit or the Carnot limit.
Thank you.
Yeah.
Any other question? Okay, since there are no other questions, let me ask you a very general query and continuing with the previous question that we have not talked about general experimental scenario about this subject, because I understand the subject is there for roughly 15 years or more than that. So there must be some experiments to verify some of the predictions and also possible technological adventures.
Yeah, so far actually technological, the experimental picture is not so rosy. But I'm hopeful that very soon there will be experiments. So there are one or two experiments, but they are not really, in the quantum domain. They have done some experiment with the, using this stochastic heat engine or so, but they were not purely quantum.
So why I'm asking is that you presented a model involving this ancilla, this XY model, right? Mm-hmm. So what is the motivation for considering this type of models? Just purely to analyze the system, or there are some similarity with some real life experiment which can be performed or something like that?
Yeah, the main motivation is, that ancilla based work is that, you are not, even if you are doing measurement, you are not disturbing the system. So my main system is the working fuel is that other two qubits, not the ancilla part. But since the ancilla is entangled with the system, so doing measurement on the ancilla, I am extracting information about the system.
No. My question is different. My question is that instead of XY model, it would have taken, say, XYZ model, spin XYZ model, right? Or XSZ model. Just motivation for considering that specific model, and then that interaction of one is magnetic field and then another is just interaction X direction. So those are motivated by some real life scenario, or just to get some result to verify the ideas?
No, it was just, to explore certain things. Yeah.
Okay. Thank you very much. Any other question?
I have one question. Yeah.
Yes, Prashant.
Yeah. See, Asoka, you talked about thermometry, but you can also think about measuring magnetic field, because magnetic field will affect the spin in this, spin models which you have considered. So it could be a very sensitive indicator of change in magnetic field.
Yeah. So actually, quantum sensing, magnetometry is already been explored in other ways. So, in this way also, magnetic field can also be done. Measuring magnetic field can also be an direction using quantum thermodynamics. Yeah, we'll definitely think about it.
Yeah, one more point. You did mention about this, loss of information and heat produced through Landauer's formula. But here, for example, in ancilla, when you extract information, have you quantified, how much of heat is being generated and how much of information is being lost?
Actually, so we did the measurement on the 2 qubit basis. So I mean, using just the formula in this is KTLN2. So 2 KTLN2. So that much. I mean, that cost we have included. So it comes in the denominator of the calculation of the efficiency. So that because of that measurement, the efficiency will be reduced little bit.
Yeah, just one small related question, and then I'll stop. See, for example,
sure.
the 2 qubit, the entanglement also will change, right? In the process, entanglement cost would also be related to this, no?
Entanglement cost will?
See, for example, when you do the measurement, you have a 2 qubit system. So in principle, that 2 qubit system could be entangled. So there would be change of entanglement and through von Neumann entropy.
Right. Yes, yeah. Yeah. Those things, yeah.
Okay, yeah. Very nice talk. Really enjoyed it. Thanks.
Okay. Thank you, Prashant.
Okay.